So we're talking here, and today is the 11th of December, about this bond length thing. And the thing to understand is that there's energy involved here. Remember, we've got two things that are racing towards one another. They're attracted. Think about momentum. If you have two objects rolling down opposite hills towards one another, they are rolling towards one another. They've got energy behind that. They've got kinetic energy. These things, you and cutie pie, are racing towards one another, and there's momentum there. And that would be this part of the diagram. So, at this point, they're racing towards one another, and there's momentum, there's energy. When they get about so close, that's when that repulsive force kicks in. And suddenly you have the protons in one atom being repulsed by the protons in the other, the electrons in one atom being repulsed by the electrons in the other. And they start to sort of get blown back apart. If you imagine something being blown backwards from an explosion, that force of repulsion, it's like hitting a wall, and whoa! And where they end up bonding is at the length where those things are, here's if they get too close, and they're completely blown backwards. So where the bond ends up happening is at the distance where those two forces are balanced. That's what determines bond length. Now, all chemical bonds are not the same length. And we're going to talk a lot coming up about multiple bonds and other things, but the length of the bond varies widely. You do not have to memorize this chart. Obviously, that would be stupid. But if you remember, here we're talking about picometers. You'll see here we have a 74 picometer bond. Here we have a 228 picometer bond. Which two are closer, the hydrogens or the bromines? The hydrogens are a lot closer, significantly closer. Look at these. This is all carbon bonded to carbon. Carbon single bonded to carbon, 154 picometers. Carbon double bonded to carbon, 134 picometers. Carbon triple bonded, we're getting much, much closer. Now, when we talk about the energy contained in those bonds, so just like a magnet has it, we don't talk about it typically as energy, but you can think about it that way. It's got this ability to do work. It's got an ability to pull an object. There is energy, the ability to do work, contained within these chemical bonds. How many of you broke chemical bonds for energy today to get to school? All of you. You specifically used a machine which breaks the bonds in long chain carbons to get energy out of them. Gasoline, diesel, one or the other. So we've got different bond lengths. Different bond lengths have different amounts of energy. Let's look at these carbons here for a second. So here we have carbon single bonded, and let's compare it to carbon triple bonded. Which one has the longer bond length? I can expand that if you would like. It's not expanding. Look at single bonded carbon. Bond length, 154 picometers. Bond energy, and this is what are called kilojoules, that's 1,000 joules, 348 kilojoules. When we triple bond carbon to another carbon, what happens to the bond length? Decreases. Triple bonds are held more tightly, they're held more closely than single bonds. What happens to the bond energy? Go up or down? Point. Up. Just a little bit? I mean, the bond length didn't go down that much. Does the bond energy go up just a little bit, or is it more significant than that? More, yeah, it's what? More than doubled? Nearly tripled? It's a lot more energy. The shorter a bond is, typically the more energy is contained in it. The more tightly those two atoms are being held, the higher the forces of attraction and repulsion, and the more energy it's got in that bond. Now, when you break that bond, where does the energy go? out into the world, out into the environment. When I said you were breaking chemical bonds this morning to get to school, when you combust gasoline or diesel inside an engine, you are liberating the energy in those chemical bonds. You're getting it back out. You're cashing the check. So I have a little story about propane. Propane. How many people here have seen propane burn? I'm going to assign you homework if you haven't. You've never seen propane burn? Really? Okay, you need to go home and ask around. Do we have anything in this house that burns propane? Grill, little torch, that works. Propane burns fairly hot. It's commonly used for grilling. A lot of people have furnaces that run on propane. Little torch for doing soldering on plumbing. It's all propane. And propane, we will not get to organic chemistry, I guarantee you, but the prefix prop, P-R-O, means 3 carbons. So it's a 3-carbon chain with some hydrogens attached. Pretty easy. And great, burns, gives us some energy. Fantastic. Now, there's something else you can get called MAP gas. Has anybody heard of MAP gas? MAP gas comes in a similar cylinder, different color. But MAP gas, well, it's also got 3 carbons. But one of them, I cannot remember it. I may get this wrong, so you can go look it up and tell me I'm wrong. I think it's a double bond. I don't think it's a triple bond. One of those carbons has an extra bond. It means you got a few less hydrogens. So when you burn propane, you are cashing the check. You are getting the energy out of those chemical bonds. When you burn MAP gas, guess what you're doing? Cashing the check. You're getting the energy out of those chemical bonds. Which one do you think burns hotter? Don't tell me. Tell the people sitting at your table. So we can think back to what we said about bond length and energy, and think about MAP gas versus propane. How many of you think the propane would burn hotter? How many of you think the MAP gas would burn hotter? Sure does. MAP gas burns significantly hotter. That's actually why they sell MAP gas. If you're doing plumbing work and you need to get a nice focused hot flame on something, very concentrated flame, it's really handy to have a torch that burns hotter than the propane torch. So you've got MAP gas. Now, I'm not going to take the time today to tell you the story about my friend Mike and his propane-powered potato cannon. He's an engineer. He did all the numbers. He ran the numbers, calculated the thickness of PVC pipe and everything that would be needed to withstand a propane-powered potato cannon instead of the old hairspray or ether or anything else. And that was great because he's a math kind of guy. And not a civil engineer, not a mechanical engineer, electrical engineer, but still got the math chops. Except then he decided to run it on MAP gas one weekend. What do you think happened? Nothing good. No one died. Except the potato cannon. Shattered into pieces, exploded, gone. All because there is more chemical energy in those double bonds than there is in the single bonds of propane. So, the takeaway is if you're going to engineer something for propane and you're going to go to all the trouble of doing the math, don't at the last minute decide to swap it out and just think that you can run it on MAP gas. You can't. Like I said, no one died, so that's good. But the shorter the bond, the higher the energy. The shorter the bond, the higher the energy. The longer the bond, typically the lower energy. So we're going to do something real quick with some rubber bands. This is where I get to throw rubber bands at you, and then I'm going to go. Okay, so I would like you all to take this rubber band and put 2 fingers and 2 fingers, or 1 finger, whatever, and just kind of stretch it. How far can you stretch it? Did anybody break theirs already? Sorry. They're a little bit old. I need to get a... Oh! That was very close. Dylan's okay. Madison's in shock, but it's okay. Okay, so these are a little bit old. Maybe you shouldn't stretch them very hard. Okay, if you've got it broken, but you still have... Don't stretch it real hard, because they're pretty old and fragile, apparently. But if you stretch it singled, mine's about to break, I can feel it, you can stretch it pretty far. If you double it over, can you stretch it as far? What if you, and this is the challenging one, what if you triple it? Ooh. It gets much harder. And look at how much tighter it is, how much more energy it takes, and how much shorter it is. Shorter bonds, higher energy. Longer bonds, lower energy. Okay? So, tomorrow we're going to start doing Lewis dots. So everything about Lewis dots is because things would like to have a full S&P. This is the Octet Rule. You probably saw it in physical science. We've sort of briefly touched on it here, but never formally. So formally, welcome to the Octet Rule. The noble gas configuration is the most stable configuration you can have. So elements are always trying to exist in that full upper S and P. And tomorrow we're going to start learning ways to notate that S and P, to draw it, basically, which will lead us into doing Lewis dot structures, which are a good way to visualize. I think for visual learners they actually help. They're a good way to visualize atomic structure. Okay, your labs, how many of you feel like you were able to answer them using your notes in the book? I'm going to tell you that you would not have been able to answer them just off the top of your head, and we haven't talked about all the concepts yet. We were working a little bit ahead. So if you didn't go to the book at all, you probably got a few of them wrong. Did you go to the book? Okay, good. So you can turn those in, and you've got the rest of the time to work on the chapter review, and hopefully I will see you tomorrow.